you don't have to let me know you're here because I don't need to take attendance, but I mean, if I ask a question, I'd appreciate it if you guys give me some feedback. You don't have to, but just it's appreciated as always. So, it's been annoying. So obviously I couldn't cover everything, but I put what people said they were struggling with on this worksheet and what I thought was tricky. So hopefully you'll find this helpful. So for this first problem, we're just drawing the 1, 2, and 1, 4 addition products to give you guys a bit more practice. You should remember the mechanism for adding HX, which is like HCl or HBr to a double bond. So like, okay, if I had this, I'm just showing like for one double bond, the mechanism. This would be like the intermediate we get. The secondary cation is what forms because that's more stable. So that leads to the Markov-Makov product. That's just a bit of background. When we have a conjugated diene and we're adding one equivalent, it's only going to react with one of the double bonds. So like we can react it with the double bond on the left, like this. And then that will put the hydrogen here, like before, and put the cation here on a tertiary position. And on top of being tertiary, it's also right next to a double bond, so it's allylic and it's stabilized by resonance. So we can add the chlorine to the cation just as is, like we did with the double bond I just showed before I started this problem. And this is the 1, 2 product because the double bond was here with carbons 1 and 2. But like I said, there's a resonance form, so we can show the electrons flowing towards the double bond. That puts the double bond here. The hydrogen we added from HBr is still here, and now the cation is here. And then the chlorine can attack that. So because of resonance, the chlorine ends up on a carbon that is on position 4 relative to the double bonds that we reacted with. So that's why this is the 1, 4 product. And you don't really have to do all this mechanism stuff unless he asked and you had to upload it somehow, but it helps to understand. But if you want to just remember, like, whatever you're reacting with, the one thing ends up on carbon 1, which is the hydrogen, and then the other thing ends up on either carbon 2 or carbon 4. I'm just gonna circle the products because there's a lot of stuff here. In the lecture, he numbered the double bonds. It depends on which one you're reacting with. So yes, kind of. Like if I numbered them from here, that wouldn't really be correct because we weren't reacting with this double bond on the right. We reacted the HBr with the double bond on the left for this mechanism I showed. So you should just, oh, it didn't go that far back. Oh, well, you should just number them from whichever one you're reacting with, and you're only going to be reacting with one at a time if you're using one equivalent. So that's just, yeah, I don't know how else to put it. Okay. So yeah, like if I react with this double bond, which is what we have to do to show the other products, then this would be, like now we're numbering from this double bond. So this is 1, 2, 3, and 4. This is the 1, 2 product. And then the double bond ends up in the same place. You can draw the resonance form to prove it, that it does. So the double bond ends up here. The hydrogen is still on carbon 1 because we're still numbering from the same spot. You know, this is carbon 4 because we were starting with the double bond on the right. So this is the 1, 4 product and the 1, 2 products that come from the double bond on the right. So unless he explicitly says draw the 1, 2, and 1, 4 products from this specific double bond, I'd assume he wants everything, but I mean, it'll depend on the context of the question. So I'm just drawing everything basically as practice. And this kind of idea also works with like adding X2, which is Cl2 or Br2. I guess to continue with this single double bond example. You do have to know the mechanism for this, but I mean, I can go over it if you want. Hopefully people remember. But this is the product that ends up forming. Just, you could think of this as 1, 2, because there's only one double bond and the chlorines are trans to each other. Well, this isn't symmetric, so yeah, we have to look at both. So we'll start by looking at this double bond. You could draw a mechanism, but this is, I feel like it might make it confusing, so it's probably easier to just look at it like instead of adding a hydrogen to one of the spots like we were with the last problem, we're adding a chlorine. So we're adding 2 chlorines basically. So if we're reacting with the double bonds that I have circled right now, this would be a 1, 2 product. And then we still have a chlorine on carbon 1, and then a chlorine ends up on carbon 4 for the 1, 4 product. And that happens again due to resonance with an intermediate. That's why the double bond moves. And it always ends up in the same spot, which is between carbons 2 and 3, regardless of which double bond you started with. So this is 1, 4, and that's 1, 2. And now we'll react with the other double bonds. It's going to be the same idea. And I'm not showing the stereochemistry for the 1, 4 product because I don't think it would be as important there. It kind of has to deal with cations at that point. And then like usually when you react with cations, you lose stereochemistry, like with SN1 reactions. So I'm assuming that follows here. So this would be the 1, 2 product from the double bond on the right. And then we end up getting the same, it's a little crowded, but this is the same product as this. So that's a bit redundant. And that's just because we were adding a chlorine on both ends. So like before, it was basically just switching where the hydrogen and the chlorine were for the 2, 1, 4 products, but here we're adding 2 of the same thing. So, oh, I shouldn't have circled everything. I also asked to identify the most stable products. So I'm gonna uncircle these. Okay, so yeah, I asked to identify the most stable products or products and consider alkene stability. So what makes an alkene more stable? What trends do we know?
It has to do with the carbocation, right? I mean, the tertiary, if it's tertiary or secondary.
That has to do with substitution, yeah. So like Michael said, more substituents, and it's the same idea as cations. So like you were on the right track, but we don't look at it as tertiary or secondary with double bonds. We just look at like how many substituents are on the double bond. So for this first 1,2 product here, the double bond has free substituents that I tried to highlight. It's just the free different carbons it's bonded to. And then this 1,4 product also has free substituents. Did I draw one of these? Oh, not all of these are products. Started confusing myself. Okay, those two are products. That's a product. Okay. Sorry. But again, this has free substituents, and then this 1,2 product has 2 substituents. So like was pointed out, the more substituents something has, the more stable the alkene is. So based on that, I'm circling the tri-substituted double bond should be more stable than that di-substituted one. And we got free that were like equally stable here just because of where the double bonds were, but it might not always be the case. There might only be one that's most stable. Just depends on the context. For the second one, this product has 2 substituents, so I guess I'll put di-substituted. This one also has 2 substituents. This one has 4, and then this is the same product, so tetra. So this, which is the same as that one, has 4 substituents compared to 2, so it's more stable. So yeah, just remember more substituents on an alkene makes it more stable, and it's the same idea for radical or a cation, so that's an important concept to remember. Number 2 is asking to predict the products, the major products for the reactions, and like I said in the email, I was wrong about like thermodynamic versus kinetic control, what I said last time. I think I learned it incorrectly when I took the class, and I just never learned proper understanding until last week. So first of all, when is something under thermodynamic control? High temperature, low. High, yes. Then it has more energy, and thermodynamics has to do with energy. And kinetics is low temperature. These are both control. So before I said thermodynamic led to the 1,4 product and kinetic led to the 1,2, and I must have heard that somewhere, but it was wrong. It's only correct when you're looking at the butadiene example, but everything else, that's not the case. So when something's under thermodynamic control, that means you're going to get the most stable products. And when we're looking at stability of products, we're looking at the stability of the alkene, in the product, which is why I added that part about identifying the major product up here, because they're the most stable, because that would be the major product if it was under thermodynamic control, because those are more stable. And then when it's under kinetic control, you get the products that formed from the most stable intermediate. Sorry, a little too big. But you get the product from the most stable intermediate, and the intermediate is a carbocation. So you're just looking for the most substituted carbocation, which you don't necessarily have to draw the mechanism, but it can help to see that like wherever the carbocation was, that's where the chlorine ended up. So you could theoretically just look for the 1,2 or 1,4 products with the most substituted halogen, and that would be your kinetic product. That's one way you could remember that. And like, I don't know how much detail he's gonna care about for these anyway. Like at most, you're probably gonna get 1 or 2 questions on this, but it's still good to get some practice. So for this first one, it's low temperature, 0 degrees is pretty cold. So this is going to be under kinetic control. So that means we're going to get the most stable intermediate that leads to a product as our major product. And this structure is symmetric, so it doesn't matter which double bond we add it to. So I'm just going to pick the double bond on the right to work with, but it doesn't really matter. And I'm going to draw both products to show you the difference between them, because I think the better way to approach this would just be to look at all possible outcomes and then just like figure out which one would fit with whatever control you have. So a 1,2 product here would be this, because this is where the double bond was, so that's where the chlorine ends up. And then this would be a 1,4 product. And you can draw the resonance, or if you really want me to, I can show the resonance that leads to this, but hopefully you can see how this is the 1,4 product. So based on what we have here, which one would be the major product with kinetic control?
The 1,4 product?
Yeah, because that has a more substituted halogen, which means it came from a more substituted cation, which is more stable than this one over here that is secondary, the 1,2. So thermodynamic doesn't necessarily mean it's going to be 1,4, and kinetic doesn't necessarily going to mean it's going to be 1,2. It depends on the substrate and what kinds of products you can get. So just put because it had a more substituted halogen. That's why that's the major product too. You have a question? Sure.
Yeah, I was just wondering, so usually the hydrogen is always added to the first position, right? In these in conjugated dienes?
When we're adding HCl or HBr, yeah. If you're adding Cl2 like we did for this question, then you're adding a chlorine because you're adding 2 chlorines. But most of the time, like if it comes up on a test, I'm pretty sure it will be HCl or HBr. So hydrogen always adds the carbon 1 because that puts the carbocation intermediate right next to the double bond, which allows for resonance.
Okay, got you. Thank you.
Mm-hmm. Okay, so this one, it's at 40 degrees Celsius. So this is going to be thermodynamic control. And I ended up using this exact substrate last time, but I'm pretty sure my answer to that was wrong. So I also did kinetic control for that. And this one is Fermo, so it's slightly different. I'm going to go over it correctly this time. So when we have thermodynamic control, we want the most stable product. So that means like the most substituted double bond. So weird looking T, whatever. But I could show all four possibilities, the 2, 1, 2 products and the 2, 1, 4. I don't think it's really necessary here though, because if we look at the double bonds we're starting with, this one on the bottom has 2 substituents, it's di-substituted, and the one on the top has 3 substituents, so it's tri-substituted. That's already pretty stable. And I guess I'll draw it over here. Regardless of which double bonds we add the HCl to, the resonance form that leads to a 1,4 product will put a double bond here, which is also di-substituted. So that's not as stable as the tri-substituted double bonds we have here. So because of that, it would make sense that because it's under thermodynamic control, we'd add the HCl to this double bond so we can keep that double bond up there, and we don't do resonance to move the double bond. So we would end up with this 1,2 product is the major product, because that leaves the double bond in the more substituted position, which makes it more stable. So again, thermodynamic doesn't always mean 1,4. It depends on the context. Hopefully that makes sense. I'm sorry I taught it incorrectly last time. I honestly don't know where I learned what I was thinking, but again, hopefully this makes sense. If you have any questions, feel free to say something, but otherwise I'll be moving on.
Yeah, actually, I was wondering something real quick if that was all right. So for these examples, like you were mentioning, the temperature will tell us whether it's thermodynamic favors thermodynamics or kinetics. But it sounds like regardless of the temperature, we kind of have to, I guess, draw both products, right, to see which one it is that's more stable.
That helps, but from like you only have to worry about the stability of the product itself if it's thermodynamic, and if it's kinetic, you're worrying about the stability of the intermediate. Do you understand why that's the case? Because I guess I didn't really explain that, but it was covered in lecture from what I could tell.
Yeah, it kind of has to do with like the stability of the carbocation and everything, like you kind of quickly mentioned not too long ago, a few minutes ago.
Well, it has to do with a reaction coordinate diagram that he probably glossed over because he didn't have much time. But
Yeah.
Just when you're under kinetics, well, basically when you're under thermodynamic control, the reaction is reversible. So like if it forms a product that's not as stable as something else that could form, it can go back to the intermediate and then go forward and form the most stable product, and that's going to be what forms the most. But when it's under kinetic control, the reaction's not reversible, so it just wants to form like what it can form the most quickly, which is the most stable intermediate, because that has the lowest activation energy. They don't really have space to draw a reaction coordinate diagram. That's why I'm not drawing this. But if you take what I'm saying and you look at what he drew on his lecture notes for the last slides, it hopefully will click. So that's the reasoning behind these rules here. So just, I don't know if I answered your question.
Oh, no, you did. Yeah, thank you. I actually remember I was looking at the notes earlier today, so I know exactly what you mean. Thank you.
Okay. So nobody else has any questions, I can move on. There's nothing wrong with questions. So like, even if I'm working on something and you realize, oh, I have a question about one of these earlier ones, just say something. You have nothing against going back for that. Okay, so most of the rest of these are synthesis, and I tried to make these synthesis problems cover as much stuff like from different topics as possible. So like alkene reactions, alkyne, SN1, SN2, and even some other stuff that's more recent. So the context out of the way. What will these first conditions do generally?
Cause an SN2 reaction.
It looks like SN2, yeah, because we have a strong nucleophile and we have an aprotic solvent. And generally, when you have a strong nucleophile and you have an aprotic solvent, the aprotic solvent is going to favor SN2 over E2, even though this is also a good base. So that would favor SN2, and it's a secondary position, which works fine for SN2, but you have to consider the position right next to the leaving group. It's a quaternary position that's a badly drawn, or I'll redo that, but because it's a quaternary, okay, because it's a quaternary position, it basically stops SN2 reactions from occurring because SN2 is like dictated by how much steric hindrance there is. And when there's a big bulky group like this quaternary carbon right next to the leaving group, that makes it kind of difficult, makes it sterically hindered. So even though like the conditions themselves look like they favor SN2, you have to double check the surrounding area, and this quaternary carbon makes it E2. So because it's E2, it's going to form a double bond, and it can't form a double bond towards the left because there's no hydrogens on that carbon. So that's the only double bond we can form. Okay, what about this next reaction? What does that do? We have NBS and water.
We're going to add a bromine and water.
Yeah, because NBS is just, yeah, we're adding hydroxide as one of the things, but also bromine. So NBS is just a source of Br2. And this is not the only reaction you've seen NBS with, but like it depends on the context of what else we're using with it. So when we have NBS in water, that's basically the same reaction as like Cl2 in water, because NBS is just a source of Br2. And it's very similar to if we just added Cl2, which I went over earlier. So the stereochemistry of this reaction is important, and also the regioselectivity. So the hydroxide gets added to the Markov-Makov position, and the two things get added trans to each other, so it's anti-addition. So this would be the product we get. The bromine on the primary spot, the alcohol on the secondary, and they're trans to each other. What will this next reaction do? It's a triple bond carbon with a negative charge. It's an acetylide ion. And we have a bromine here on the primary position at the end of the chain. Yeah, thank you. So it does an SN2 reaction to kick out the bromine. And it wouldn't react with the alcohol because one, that's a secondary position, and two, that's a bad leaving group. And this reaction only works with primary alkyl halides. So the alcohol is still here. And we get this. So you should make sure to count your carbons when you do this. We had 2 carbons like off to the side of the terbutyl to the beginning. And we were adding 3 carbons. So like 1, 2, 3, just making sure that's correct. So that's the product. And then what does this last reaction do? We have ozone and then zinc and acid. Yeah, it cleaves the bond. So we can draw a line through the triple bonds to kind of help us see what we're doing. And what kinds of products are we going to get when we cleave this? The alcohol's still here. Yeah, we're going to get carboxylic acid. So I basically just drew the structure on the left, and then at the position where the triple bond was, I put a carboxylic acid, and then the same thing with the structure on the right. So this would be the products. And even though we used ozone, it doesn't matter what you use to cleave a triple bond. So we could have used ozone or KMNO4, and they both would have led to these products. But if we were cleaving a double bond, it would be a different story. So like if you cleave a double bond of ozone, you get aldehydes, not carboxylic acids. So it depends on what you use there. Just wanted to highlight that because that's important. So are there any questions about this? Doesn't look like it. Okay. If I ever go too fast and you just don't have time to ask again, just say something still. All right, so this is filling in the reagents instead of filling in the products. So how could we get from this double bonds to this first product here? Kind of went over it already. I pointed out that this is very similar to the NBS and water reaction.
Should be HCl and water, right?
Not HCl, but Cl2. If you use, actually I'm not even sure what would happen if you used HCl and water. I'm pretty sure it would just add the H in the chlorine. So it should be Cl2 and water. Guess I can go over the mechanism quickly, because you do have to notice anyway. I'll draw it over here, I guess. So we basically form a little cyclic ring with the chlorine, with the cation kind of shared between everything. And then when we have this, instead of a chlorine attaching, which is what would happen if it was just Cl2, the water is what comes and attacks, and it attacks the more substituted position to lead to the Markovnikov addition of the alcohol. and then the water gets deprotonated by that Cl minus. I'm not going to go over all of that, but this is what's important to remember. Just these first two steps with the cyclic ring forming and then the water attacking. But if we used HCl, then I'm pretty sure the chlorine would be what's attacking the cation because water is not a very strong nucleophile, so it wouldn't really matter that it was there. Okay, so these are the conditions. And now we're going from a alcohol and a halogen right next to each other to this. What is this called? It's called an epoxide, yes. And there are two ways, to form this. One of them is directly from a double bond, and then this is the other way. Does anybody remember? So yeah, that would be if we're reacting with a double bonds to form an epoxide, but we're not starting with a double bond here. We're starting with an alcohol and a halogen right next to each other. So we can't use MCPBA. We have to use something else. Actually kind of know the mechanism for this by now. Imagine like have a chlorine here and you react it with sodium hydroxide. COH would just substitute for the chlorine and kick the chlorine out. So that would be an SN2 mechanism because we had a strong nucleophile kick out the leaving group. But here we have, well, it's an alcohol right now, so it's not a strong nucleophile yet, but we can do something to turn it into a strong nucleophile to give it that negative charge. So how can we give the alcohol a negative charge? Alcohols are acids and bases. If we use a base, that will work. So that's what I was trying to hint towards. And KOH is usually used for this. And methanol is used as a solvent. But so basically what happens is the base deprotonates the alcohol, so you get a negative charge, and then it kicks out the chlorine, and now the oxygen is attached to both carbons, and this is basically just an intramolecular SN2 reaction. So intra is just saying inside, the reaction is occurring in the same molecule instead of between two molecules, like what you normally see. You don't really have to know all of this. You don't even have to know that this is the mechanism for this reaction, but hopefully the fact that I've shown this to you helps you remember that, like, if you're trying to get from an alcohol and a halogen to an epoxide, then you're going to want to turn the alcohol into a nucleophile so it can do this reaction to form the epoxide. And to turn it into a strong nucleophile, you'd want to use a base. So hopefully that makes sense. But if you just wanted to go from the double bond straight to this, then you could use MCPBA. That's just not how I phrased it. I gave the question. Okay, so how can we go from this epoxide to the next product, this 1,2-diol?
Yeah, oxymercuration.
So that's a reaction we use to react with double bonds by themselves, and that adds one alcohol. So, like, you have the right idea that we're adding alcohols, but um, it's not the correct substrate, basically. We're starting with an epoxide. So this is basically just you either know it or you don't, and nobody has any guesses, then it doesn't seem like it. Okay, so practicing these kinds of questions with the alkene, I think that would work, but you're going to learn next semester that there are multiple ways to open epoxides, and depending on what you use will affect what kinds of products you get. In terms of what you've learned this semester, I'm assuming he's just going to want to stick to what he showed you, which is using an acid, so H3O plus. But KOH also opens epoxides, just like if you were given multiple choices, I'm pretty sure the acid would be the correct response this semester. And the way that works, well, you don't really have to know the mechanism, but the epoxide gets protonated and then one of the double bonds breaks. Well, not double bond. I can go ahead and show it. But the acid protonates this. And again, you don't have to know this because it wasn't shown to you during class, but kind of helps to remember. So because that double bond broke, we have a cation here, and it doesn't really matter if this is a dash or a wedge. But that was a good guess with the KOH. Jared, I wasn't trying to say like that was way off. That's actually correct. Just with what you know, you wouldn't necessarily know that yet. But like in order to get this proton, the oxygen deprotonated the alcohol, the acid. So now we have water, and the water can attack the carbocation. Actually, no, it doesn't happen exactly like this because then they wouldn't be trans. So, sorry, that was not entirely correct. This does get protonated, and then we get a positive charge that is kind of shared in between all three things, just like the Cl2 that I drew on the left here. So then it's basically the same as the water attacking that cyclic intermediate with the chlorine, but instead of it being a chlorine, it's an oxygen. And I'm not gonna draw the intermediate actually, because like you end up with an alcohol on one and then the water gets deprotonated and you're left with that. So that's why they're trans. So this is how you would form a trans 1,2 diol. And it's a 1,2 diol because we have two oxygens, which are called, well, like the way you name them is with an ol suffix right next to each other. They're trans because they're trans to each other. There's another way you guys learned how to form 1,2 diols, which I believe comes up later, so I'm not going to go over it right now, but this is how we form trans 1,2 diols. You form an epoxide and you open it with acid. Right, now, how can we go from this 1,2 diol to this product here, where we have a chlorine over here? We only substituted one of them.
I remember you mentioned we lose stereochemistry with SN2 reactions. So it's got to be a strong acid, I'm thinking.
I think you, like, it sounds like you had the right idea, but you said SN2. I think you meant SN1. So yeah,
Yeah, I'm sorry. That's the one I meant because of the
because you said
loss of.
strong acid, and yeah, that's all correct. So SN1 reaction, what are the conditions for that with an alcohol?
It has to be weak or neutral.
Yeah, so what are we going to use to substitute a chlorine for the alcohol here? We'd use SOCl2 if we were doing an SN2 mechanism, so that would be if we wanted to replace this alcohol with a chlorine and not the other one, because then I would favor this one. Water, well, we want to have something that has a chlorine that can like substitute there. So normally SN1 prefers like acidic conditions. Yeah, so HCl is an acid, and THF is usually the solvent for this that's written in the book. So that's just what I'm putting here, but the solvent's not really important. So if you want to substitute a halogen for a tertiary alcohol, you use HCl, and that does SN1. And if you want to do a primary or secondary, you want to do SN2, and that would use SOCl2. So it depends on which one you were trying to react with. And here we were only reacting with the tertiary one. Like George pointed out, I also showed the squiggly line to show that it lost stereochemistry, which is a characteristic of SN1 reactions. So hopefully that makes sense in retrospect. Like I said in my email, I made this tricky on purpose. I don't know how tricky his synthesis problems are going to get, but if you understand my explanation, that's good, at least. Okay, so last step for this synthesis, we added some carbons here. What kind of reaction can we use for this?
Could we use the Grignard reagent?
Not Grignard, but Gilman. We haven't really looked at Grignard this semester. You might have mixed up the names because they do sound very similar. So yeah, CuLi is the Gilman reagent.
Yeah,
So
it's exactly the one I had written.
This would be a Gilman reagent and a Grignard, just for context, because you might have to know, like, identify what is this. Well, I won't put BR, but X is a halogen. So like we have carbons, and then the carbon is attached to magnesium, which is attached to a halogen. So this is Gilman, and this is Grignard. And as far as I remember, you only have to know how to form a Grignard reagent. You don't have to know anything else. And I guess you have to know, like, being able to identify it, but don't worry about reactions with it. This, however, is very important because we use it to form carbon-carbon bonds. So this is one way to form carbon-carbon bonds, and the other way is with acetylide anions, but acetylide only works with primary positions, which we don't have here. We have a tertiary halogen, so we couldn't use it. So we'd use this. We are adding 4 carbons here. I just counted them, and they're in a straight chain. So R is just equal to whatever you're adding. In this case, it's just linear butane. And then the solvent, I think, is important, but like if you're given conditions for like a matching question, it wouldn't really matter that the solvent is THF. I'm pretty sure this only works with ether solvents, so like maybe you can make that a multiple choice question. but don't worry too much about that. That's getting into fine details. So we just have 4 carbons, and then there's 2 of them because there's 2 R groups in the CuLi, and that would be the conditions to get that. Okay. So hopefully explanations made sense. Right. Now, how do we go from a single halogen to a double bond here?
E2 reaction with like potassium hydroxide, maybe.
Yeah. And we'd want to use a solvent that would make it so we don't have SN2 competing with it. So what kind of solvent would we use?
This is where I get a little confused.
Any protic solvent, yeah. And most commonly for this is ethanol, just because that's a pretty common solvent in the lab, I guess. Because E2 works fine with protic solvents, but SN2 is slowed down a lot by protic solvents. So, and this is protic because it has a hydrogen on oxygen. Well, it's protic if it has a hydrogen on oxygen, nitrogen, or sulfur. It's oxygen here, and that just has to do with hydrogen bonding. So this is protic, it disfavors SN2, so this will do E2 only, and it'll form that double bond. Now how can we get that halogen, that bromine there? We're not reacting with the double bond, but we're doing a reaction related to the double bond.
Would it be a allylic reaction?
Yeah, so what are the conditions for that?
It's NBS and the mu for light.
Yeah, NBS and H nu, and the solvent is tetrachloromethane. But the NBS and H nu are what's important. This is just signifying using light to activate the reaction, which means it's going to be a radical reaction. And that is what leads to the bromine attaching here at the allylic position, because the allylic radical is the most stable radical. So this is where the bromine ends up. If we had used the other NBS reaction I pointed out earlier, just like to differentiate the two, because it's an extremely big difference. See, these two products are very, very different from each other. So even though they both have NBS, the other conditions we're using make a big difference. So you should like remember both of these reactions, but remember that there's a big difference. One of them reacts with the double bonds to add a bromine and an alcohol, and the other one, the reaction's related to the double bonds, but it keeps the double bond intact, and it adds a halogen in the allylic position. Okay, now how do we go from that bromine to another double bond? It's actually kind of, yeah, it's the same as that first step we did. So we can just use the same exact conditions to do another E2. And it would form a double bond going this way instead of towards the other double bonds, because there's no hydrogens left there, and that would also be a pretty unhappy carbon with 2 double bonds attached to it. It'd be pretty messed up. Right, now this step I think is a bit tricky if you don't consider all your options, including new ones. Does anybody have any ideas on how to do this?
It looks like it's something about dyes.
Yeah, we have conjugated diene, and we're doing a 1,4 addition, yes. So we're going to want to use one equivalent specifically because we're only reacting with one double bond, and we're using HBr. And it's the 1,4 product, like Jared pointed out, because like the double bond was not in this position for either of the double bonds we started with. So resonance happens and we got a 1,4 product. Is this under thermodynamic or kinetic control? Because that's important too.
Thermodynamic.
Yeah, because we have the double bond being tri-substituted, which is more stable than either of the double bonds we started with. And on top of that, the halogen is on a primary position, so the intermediate probably wasn't very stable, so this wouldn't be what we got from kinetic control. So because of all that, it's thermodynamic. So what temperature would we run this under? Yeah, 40-ish degrees C. I don't know if you'd incorporate this reaction in a synthesis problem, but in the event he does, you've seen it. So if you start with a conjugated diene as some step in the synthesis, and then you end up with only one double bond and the halogen, then it was probably a 1,2 or 1,4 addition, considering the temperature is important. Because if we ran it at 0 degrees, we'd also get this product, but not as much, which wouldn't be ideal. Okay, now we're reacting with the double bond to form a cyclopropane. Does anybody happen to remember the conditions for this?
I want to say this is the reaction that has to do something with iodide, if I remember correctly.
Yeah, there's iodide in it. Yeah, that's correct, Franklin. So, like if you were given a list of reagents, if you remembered it had iodine, that's probably going to be good enough. Because I don't think anything else really uses iodine this semester. And these are the conditions, CH2I2 and zinc copper, that will react with a double bonds to form a cyclopropane. Okay. Now how can we get from this reagent to that product? SN2, yeah, what kind of nucleophile are we using?
Acetylide.
Yep, and how many carbons are we adding? Because that's important.
3.
Yep, so actually 2, yeah, so it's easy to miscount, but like we start with 1 carbon here and we can like number that same carbon as number 1, and then we have 2 free here, so we only added 2. So it's really easy to miscount. That's why I'm just like trying to emphasize count your carbons. So we're adding 2. It's just going to be this kind of thing. So it's just 1 triple bond with the 2 carbons, and then one of them is deprotonated, and the solvent is going to have to be an ether solvent, just THF usually. So that'll lead to this product. Now, how do we reduce the triple bonds to a double bond? What else? Like, you're correct, Lindlar's catalyst is part of it, yeah. So H2 and Lindlar's catalyst. Is that the only thing we can do? Or is there another way we can get this? Yeah. So, yes, I'll just draw another arrow. Why do both of these work here? Because they do give different products normally. Well, it's not that it's not specified, it's that the double bonds here can't have stereochemistry, actually. But yeah, you were on the right track. So this can't have stereochemistry because there's two hydrogens here. So because there's two of the same thing on one side of the double bond, we can't really say like this H is cis to one branch and then the other H is trans to it because they're the same thing. So there's no stereochemistry. But what does Lindlar's catalyst lead to? Because you do have to notice it just wasn't relevant here specifically.
Yeah.
And then, so Lindlar's catalyst leads to the cis double bond, and then La and NH3 leads to the trans double bond. So that's just something to keep in mind. Okay, now how do we go from that double bond to this 1,2 diol? Specifically, cis.
With osmium tetraoxide.
So this is a, I'm gonna erase those hydrogens there because they're kind of in the way, but it was just for demonstration. This is a two-step thing. The first step is OSO4, and the second step, that's not entirely correct, sorry. It's NaHSO3. Boy, okay. All you really have to remember probably is the osmium tetraoxide, but it is a two-step thing, so both steps are important. And osmium tetraoxide leads to a cis 1,2 diol. So this is the other way to form a 1,2 diol. The other way we went over earlier was ring opening and epoxide, and that gave a trans product. So the product you end up with for the 1,2 diol, like depending on the stereochemistry, you're going to use a different path to get there. All right, and now the last step, how can we get to that product? I'm gonna point something out.
There's an aldehyde, so we're cleaving something or oxidizing.
Yeah, we're gonna be cleaving it because we had free carbons on this right side of the chain from everything else before. Now we only have two, so I didn't show the other products to kind of try to get you to think about it and count the carbons to see that there were a few less. But once you recognize that there's less carbons, you should recognize that it was a cleavage reaction and we're cleaving this bond. There's a reaction you guys learned for cleaving the bond between a 1,2 diol. Does anybody remember what it is? So I actually forgot, like, this is a reaction that uses iodine, so maybe don't just remember that the cyclopropane is the only iodide one because this is another one. This is used pretty rarely, so it's okay if nobody remembers it, but you should try to keep it on your radar for next week. It's HiO4 and water. These conditions will cleave a 1,2 diol, just as if there was a double bond between the 1,2 diol. And you can see that it formed an aldehyde, so it cleaves the same way as if you used ozone on a double bond, basically, because ozone also leads to aldehydes, but if you use KMNO4 on a double bond, you get carboxylic acids. So just remember that if you cleave a 1,2 diol, you're going to end up with aldehydes, not carboxylic acids. And then just to show what the other product would be, it's formaldehyde, because there's just that one carbon over there. It gets turns into a carbonyl group, and then there's two, like it's an aldehyde, but there's only one carbon, so it has two hydrogens on it. So if I had given you that, it probably would have been super obvious it was cleavage, but it's possible he could give you just one product like this, but there's less carbons, so you should recognize that it's cleavage. Are there any questions about any of these steps? This was a really long synthesis problem, but it incorporated a lot of what you've learned this semester, so hopefully it was helpful. Doesn't look like it, okay. So this last one is just a few, hopefully tricky questions. So you have to figure out what the product is going to be, and to do that, you should figure out what the mechanism is going to be, or determine that it's not going to have a reaction. So for this first one, what's going to happen? What kind of mechanism are we going to do? So let's go over it. It kind of looks like it would be no reaction at first if you look at the conditions. We have a primary leaving group, and we're using methanol. So what kind of nucleophile is methanol, strong or weak?
Weak.
Yeah, and it's also the solvent. So what kind of solvent is it? Protic or aprotic? Yeah, protic. So these two are looking like it's going to be SN1 or E1. And we have a primary position, so that usually doesn't work with SN1 very well. So I'm assuming that's why you would say it's no reaction, but you also have to consider like where is the leaving group and what happens when it leaves. So suppose it left. The mechanism for an SN1 reaction is like just the leaving group leaves and then you get a cation. This cation is right next to a benzene ring, so it has resonance. It's a benzoic cation, so it's stabilized. So I'm not gonna draw all the resonance forms, but there's like 4 resonance forms. And what does resonance do to things? It makes them stable, yes. So because the leaving group is benzoic, even though it's a primary position, the fact that it's benzoic makes it possible to do SN1 or E1. So if a leaving group is benzoic or allylic, even if it's primary, it still works for SN1 or E1. So that's something you have to be mindful of. Don't just assume that because it's primary, it's going to be SN2 or E2. Yeah, so hopefully the facts that like if you were to draw the cation and you see that it's allylic and stabilized, that would help remember. Okay, so now we know that it's going to be SN1 and E1. Can we draw an E1 product for this? Is that possible? Is there a neighboring hydrogen that we can take away to form a double bond with? No, so yeah, it's only going to do the SN1. And I was emphasizing that just because if he was asking what mechanism would this substrate follow, then it would only be SN1, not E1, because it can't do E1. Even though like both of them happen at the same time, if there's no neighboring hydrogen, it can't do E1, so that's not correct. So we get E for product. What about this second one? What kind of mechanism is it going to do? It kind of looks like it would be E2. So let's go
E1.
over it just like, what were you going to say, George?
I'm sorry, I was just thinking it's E1 because you're saying it looks like it would be E2, but it's a weak acid.
Yeah, but let's go over the whole process to figure out what it is. So, like, you're both on the right track, I think, but this one is a little tricky on purpose. This one is very tricky on purpose. So the position is primary, because that's where the halide is. Like George pointed out, this is a weak nucleophile and a weak base. And you can remember that two ways. Like if you draw that structure, that's an acetate ion. It's pretty stable because it has resonance. So because it's stable, it's weak. So it's a weak nucleophile and a weak base. So it's not going to do SN2 or E2 because it's weak. And on top of that, you could remember like this is the conjugate base of acetic acid. And acetic acid is one of the stronger acids. You don't really have to remember like the pKa's of things, but you're going to see acetic acid a lot and it's a strong acid. And the stronger the acid is, the weaker the conjugate base is. That's something that is going to come up on the final, so that's a concept to be aware of. So that's just kind of an aside explaining why this is a weak nucleophile. The solvent is protic, so that makes it look like it's going to do SN1 and E1. But this is a primary position. And is this allylic? No, it's not. It looks kind of like it is, but it's one carbon too far away from the double bond. So it's not allylic. So because of that, the conditions favor SN1 and E1, but we can't do that because of the substrate. So there's just no reaction. So sometimes all the factors are important, the substrate, the nucleophile, and the solvent. Like the substrate and the conditions you're using are competing with each other, so you just don't get a reaction. So that's something to be mindful of. And normally if you see sodium, it's going to be a strong nucleophile or a strong base. This is like the only time that that's not the case because of the resonance like I showed you. Okay, what about this next one? We have alcohol reacting with sodium cyanate and DMF. Do we have any guesses on what it is? And why is it no? Yeah, that's correct, Michael. So this is another very tricky one. Like I said in my email, I made this difficult on purpose. So it looks like it's SN2 because we have a secondary leaving group. We have a strong nucleophile, which is also a weak base. So NaCN favors SN2 over E2 because it's a weak base. And DMF is an aprotic solvent. So all of that is looking like it's going to do SN2. But the problem is the leaving group is hydroxide, and when this leaves, well, the leaving group is an alcohol, which forms hydroxide when it leaves. And hydroxide is a terrible leaving group because I mean, we use sodium hydroxide as a nucleophile for these reactions all the time. I, I have an example way up there, but I don't want to go all the way up. But the fact that we use it so often, like we use it because it's a strong nucleophile, it's very reactive. So when it leaves, it would just probably go back and kick out the cyanate. So it doesn't stay gone. It's a bad leaving group. So because of that, this would be no reaction. Generally, when we have hydroxide as a leaving group, we're doing SN1 or E1. And that works because then the alcohol gets protonated because we're using acidic conditions and then it's water, and that's a great leaving group. So if you're trying to do SN2 or E2 with an alcohol, it's basically not going to happen because it's a bad leaving group. It has to be converted to something better. So yeah, another tricky one. Now what about this last one? What kind of mechanism is it going to follow? Yep. So secondary, nothing wrong with it. What kind of, well, I already said the answer. So we have a strong nucleophile, which is also a strong base. So at this stage, the fact that it's a strong base means that it could potentially do SN2 or E2, and it would be competing. And when that's the case, then the solvent is the determining factor. What kind of solvent is this? Yeah, it's acetonitrile. This is aprotic. So most of the solvents that are aprotic are weird acronyms like DMF or DMSO, but there's also acetonitrile and acetone and THF. These are also aprotic. So just don't just remember that the acronyms are aprotic. There's also these free that could potentially come up. But because it's aprotic, that favors SN2 over E2. Well, E2 also works, but as far as I know, based on what you guys learned, like if these are what you have, then it's gonna have SN2 as the primary product. And what's gonna happen to the stereochemistry? You have a dash at the beginning, it's gonna reverse. So we started with a dash and we end with a wedge. I won't draw another arrow, but like, suppose we'd used, I guess we'll do it over here. Sure. Suppose we'd used methanol as our solvent, then this would have been protic. So that would have disfavored SN2, and it would have done E2. So that was just a point I was making a minute ago. Like when we see that it's a strong nucleophile and a strong base, we're using the solvents as the determining factor. And what's going to happen? If it's aprotic, it'll be SN2. If it's protic, it'll be E2 because E2 doesn't care. So if that had been the case, then we would have gotten this as our product. So like this wasn't the question, but I'm just pointing it out because it's important. The solvent is the determining factor sometimes. Okay. Any questions on these last four? And number 5. Those middle two were very tricky, but hopefully my explanation makes sense. I guess not. Okay. These last 3, I don't really want to go over everything. Like the main reason I put these here was to get you guys to think about like if you want to practice these free ideas, you don't really have to seek out questions in the textbook or online necessarily. Like, there's lots of molecules in the textbook, and there's lots of molecules on the worksheets I've given you. And you can just look at those, and if you want to practice naming, you can just pick one at random and name it. Or if you want to like determine R versus S, you can look at all these SN1 and SN2 worksheets and figure out like what the chirality is, or look at some double bonds. Like, we can go over a few of them, and I'll do that on my other worksheet just so this one doesn't get super cramped. But like, the point of this was just to get you to think, if you want to practice something, you can just look at random structures. So like something like this first one for number one, we probably could name that, but that would be more complicated than what you're going to see on a test question in terms of naming, probably. That's a bit of a pain to name. But this could potentially be something that you're asked about. So I guess I'll give you like a minute and try to name this, and we can go over it. And whenever you get something, just feel free to say it in the chat. If everybody ends up giving up, okay, so yeah, that's correct. So we're working with two double bonds, and like this is a bit tricky because like if we looked at this chain, it's 5 carbons long, and that's longer than what you named, which is 4 carbons long. But the problem with this is it doesn't include the double bonds. So when we're naming alkenes and alkynes and like anything else, like whatever the functional group that's most important is, like that, the parent chain has to be the one that includes the functional groups. So in this case, the 2 double bonds. So like this is the parent chain basically, instead of that first one that I was looking at. And we specifically start numbering from this carbon instead of starting from the top because of alphabetical priority. This is an ethyl group versus a methyl group. E comes before M, so that's just the reasoning behind that. So the name Jared gave was correct. It's 2 ethyl, 3 methyl, 1 free. Oh, well, you named it the other way, but like both of them are correct. I prefer naming it like this. The one in the free are referring to the diene part, and then the buta is the 4 carbons. But 2 ethyl free methyl but, 1 free ene. Well, okay. So slight problem with that, but I'll address it. So these are just saying the beginning is the same. So methyl. So you should put the A and then the 1 free, and then diene. Like it's important to put the di to emphasize that there's 2 double bonds. I know you have the one in the free, so that seems kind of redundant, but IUPAC is IUPAC, and that's just the correct way to name it, to emphasize that there's 2. But you were very close, and if it was like down to a multiple choice question, I'm pretty sure you would get it anyway. So Yeah, but this is the name. So that's just one example. I don't want to go over everything, like I said, but and a lot of these we can't name, so let's just do this in terms of naming, and then I'll go over some RNS stuff, and then alkene, stereochemistry. But go ahead and try to name this, and let me know when you have an answer. This one's pretty, actually no. Well, if you already started, go ahead and give me the name for that, but I think this is a better way to practice. Yeah, 2-methyl but 1-free diene, well, buta 1-free diene, but yeah. So start numbering from here, because that puts the methyl group at carbon 2. So that would be for this one on the right. And what about this circle structure I have here? Yep, that looks correct. So again, we start numbering from the side closer to the double bond. So this would be the way we number it. If actually, I think we would, because regardless of which side we number it from, the double bond's going to be at carbon 2. We'd want to give higher priority to the bromine over the methyl group there. So I believe we'd start numbering like this. This is a bit tricky, so like don't worry about it. Which like this is part of why it's good to practice, because it's been such a long time. Yeah, that and halogens, well, pretty much all the halogens come before methyl groups, but just like in general, you should give priority to halogens over alkyl groups in terms of numbering, as far as I know. I think that's a rule in the book, but the alphabetizing helps, remember that. So this would be 1 bromo free, and I'm gonna circle this to emphasize that it's separate. Can we say anything about the stereochemistry of this double bond, by the way? Can we say if it's cis or trans? Why not? You're both correct. Yeah, we have 2 methyl groups, just like the 2 hydrogens I pointed out earlier. There's 2 methyl groups, so no stereochemistry. So this is the name for this. Okay, so there's a lot of stuff on this worksheet, like the cyclopropanes. I honestly don't know how you'd name the structures with these, but there's some other structures that you could practice with, and you can look at anything in the book or anything on my worksheets to practice. So this was just to get you in that mindset, basically. Number 7 is asking to identify chiral centers and then determine if they are RRS. Pretty sure we can do that with everything in this worksheet because there's not too many. So for anything where there's not substituents like a methyl group or a halogen, there's not going to be chiral centers, so we can just ignore these first two. And this. and this because there's just no spots like that. What about, okay, just trying to get rid of that streak I made. What about this structure? Is that position chiral of the chlorine?
Yes.
Yes, it is, because it has a chlorine, a methyl group, a hydrogen, and a tert butyl attached to it. It has 4 different things. So to jog your memory, in case anybody forgot, in order to be chiral, it has to be sp free hybridized. So that just means no double or triple bonds. And it has to have 4 different substituents. Which, like I pointed out, we have here. And then when we want to determine if it's R or S, we have to rank the priority of the substituents on the chiral center. So here, what gets priority number 1?
The tert butyl group.
That does get high priority, but the first rule for the Kahn-Ingold Prelog rules is like higher atomic number is higher priority. Yeah, so based on that, we're looking at chlorine versus carbon. Those are the other 2 substituents, and chlorine has a higher atomic number. So, like, even though there's more atoms on the tert butyl than the chlorine, the atomic number of the chlorine comes first, so it gets number 1. But then, like, once we're comparing the 2 alkyl chains, like, what we can do is look at the carbons and then, like, cross one out and look at what's attached to those carbons. The carbon on the right, like, it's just a bunch of hydrogens. The chain ended. Well, the tert butyl has more carbons attached to it, so like you could consider like the atomic number of the carbons is higher than the hydrogens attached on the right. So because of that, this gets number 2, and that gets number 3. And then the hydrogen attached to the chiral center gets number 4. I'm not going to draw that in. So when we're determining R versus S, you draw an arrow from 1 to 2 to 3. And you look at what direction it's going in to determine if it's R or S. What is this?
S.
Yeah, so it's going clockwise, which like normally would mean that it's R, but like the way we determine if it's R or S is we look at the structure with number 4 pointing towards the back. But right now, I guess I will draw it in. Number 4 is pointing towards the front. So whatever it looks like, we just flip it so it looks like it's R, but it's actually S. If the coin was on a wedge, then it would be R. So yeah, that's really old stuff, but hopefully this is jogging your memory because it will come up. Great. What about this molecule? It's a bad circle. But is this position chiral? Does it have the arrow on?
Yep.
It looks like it at first. This, okay, it did that again. This is kind of tricky. So, yeah, so we have the alcohol and we have a hydrogen on a dash, I guess, and then the alkyl chloride there. But then, like, if we look at the rest of the chain or the cyclic structure, like this is a substituent and this is a substituent, and they kind of overlap at that carbon at the end. but like these two are, you can basically think of them as ethyl groups, I guess, and they're both ethyl groups, so it's the same thing. So because of that, they're the same substituent, so it's not chiral. So like in general, I'm just gonna say X is like a substituent. Like this isn't chiral, even if you have like an alkyl chain like this, it's still not chiral because the cyclic structure makes it so there's two of the same substituent. If I put a methyl group here, now it would be chiral, unless I also did this, but I don't think you'd do that. You'd probably only put one for the other. And what if I did this? Is it chiral right now?
Yeah, now it would be.
So it kind of looks like it is, but again, like if we, like we can't really look at it like this. Well, I guess we could look at it like this, but then we see like these two and that are overlapping, kind of messy, but they overlap at that carbon at the opposite end of the cyclic structure. So they both kind of have that methyl group as part of their substituent. So it's still the same thing. So the methyl group has to be like not at the op. Okay, did not mean to erase the whole thing. But the methyl group has to be like either here or here, not at the opposite ends to make it chiral. And that kind of goes back to the near plane in the molecule. Like the fact that it's symmetric makes it so it's not chiral too. So hopefully this is ringing some bells. I'm assuming you guys have finals this week, but like just review old stuff and hopefully this will come back to you. You can always look at the old worksheets for practice again. But yeah, and the chlorine at the end of the chain on this molecule of the alcohol isn't chiral because it has two hydrogens. Okay, it's the same idea of the chlorine here. It's not chiral because of two hydrogens. What about this position here? Is that chiral? Does it meet the criteria of being chiral? It's sp free. It has, yeah, so it has bromine, a hydrogen, a methyl group, and then I guess I call that an isoprene, but you don't have to know what that is. Just there's four different substituents. So yes, it's chiral. I didn't give dash or wedge for this, so we can't tell if it's R or S, but suppose that's fine. I'll be uploading the rest of this, so you can always just watch like the last 20 minutes of a YouTube video I upload to see what you missed if you're interested. But thank you for attending and good luck on your finals. And yeah, thank you. So this is over the time of the normal workshop. I don't want to keep you guys too long, and I also want to get back to studying for my finals, so I don't want to keep you guys too much longer. So I'll just go over this in like one or two alkenes for stereochemistry. But anyway, like suppose this was a wedge. It wasn't given like that, but if it was, then we would number the bromine as like priority one because it has the highest atomic number. And then the group on the left gets a higher priority than the methyl group because of the double bond here. And then the methyl group gets priority free because it has a higher atomic number than hydrogen. So this is the arrow we draw from 1 to 2 to 3. Is it R or S? Yes, it's R. Because it's on a wedge, so hydrogen number 4 is in the back. We don't have to flip it. So it's going clockwise. It looks like what it is, so it's R. Okay. So yeah, like just like with the naming, you can look at any random structure and like determine if it's chiral and then determine if it's R or S if you want to practice. And last, I just want to, I'm sure there's at least one double bond here we can look at stereochemistry for. This one here is not, like it has no stereochemistry because it has 2 hydrogens. So 2 of the same thing on one side makes it not possible to have stereochemistry. And that doesn't have any. Those don't. Okay, here's one. So this can have stereochemistry because both sides have 2 different substituents on them. So what would that double bond on the right be? Would it be E or Z? So remember E, I'll go ahead and put this. E is for, no, E is for cis. Wait, oh shoot, you're right, my bad. I messed up, so you're correct. I don't know why my brain flipped. Yeah, thank you. It's okay to point out when I'm wrong. Yeah, that's how I remember it too. I was gonna get to that, and that's probably when I would have recognized I was wrong. So E is trans and Z is cis, and like Michael said, you can remember that because you can say like Z, same side. And then if you want E opposite kind of rolls off the tongue a little bit, but Z same side is probably better to remember than E opposite. So this is trans because the hydrogens are pointing in opposite directions, so the lower priority groups are pointing in opposite directions, and the way we number the priority for double bond stereochemistry is the same rules as for RNS. So like this alkyl group gets a higher priority than the hydrogen, and then the rest of the molecule here gets a higher priority. So this is pointing up on the right, and it's pointing down on the left. So it's a trans double bond or E. And yeah, that's just the kind of process you do. You look at both sides of the double bond to figure it out. If I look at intermediates in that one question, I think there's some, just for like one extra example. Nope, never mind. Okay, well, I guess that was basically the only stereochemistry double bond we could look at in this worksheet. But like I said, the point of this question was to get you to think if you want to practice doing this, just look at random structures. So that's all I have. I guess I'll go ahead and end the recording.